important properties to satisfy. So first of all, we want the statistical distance measure to be able to support implicit distribution that have no analytical probability density functions. So what I mean is for lots of statistical model, we actually need to assuming we know the parametric form of the distribution. For example, is a Gaussian for real value data or Poisson for count data. But the idea of implicit distribution is that you may not necessarily know the probability density function, but it's quite easy for you to generate a sample from this distribution. Okay, so the idea of easily sample but not necessarily know the density function seems to be a very powerful idea. Okay, and which we're going to demonstrate that as well. And the second property, in my opinion, is that we want allowing the distribution to have a low non-overlapping supports, which means even if this distribution, they have many regions overlap, but in certain region, one distribution has no density, but another distribution has a high density, we are still able to measure the difference. Okay, but for many existing statistical distance, this is not supported. Okay, and another property I would say is we should be simple to estimate and stable to optimize. Okay, and the final property I suggest to have is we want to be able to providing unbiased sample estimate of the gradient. Okay, we want the gradient, we want the estimation of the distance and its gradient be unbiased when we only have a mini batch from the data. Okay, so to satisfy these four desirable property, I will discuss later that this basically require us to think about a new way to measure the difference between distributions, to go beyond the existing distance measure we know, like KL divergence, Jason-Shannon divergence, and Weierstrass distance. Okay, so any such kind of distance measure or will be able to providing tremendous opportunity for us to improving not only existing machine learning algorithms, but also creating powerful new methods and the inference algorithms. Okay. So let me briefly mention, so one important application of being able to measure the difference between distribution is we're able to use that as a guidance to train generative model. So what's generative model? Simply stated, given sample from a distribution P that you're trying to fit. Somebody is controlling my slides, or I can no longer see my slides for some reason. Do I need to reshare or?
Yeah, I couldn't see your slide anymore.
Okay.
Could you reshare?
Okay. Yeah, that's let me try to bring it back. Hello, are you able to see my slides?
Yeah, I can see your slide.
Okay, cool. Let me make the full screen. Yeah, for some reason I suddenly disappeared. So sorry for that. Okay, enter full screen. Okay. Let me go to. Okay, feel free to interrupt me if there's any problem with the presentation or with the video. Okay, sorry that I'm not very familiar with the team setup. Okay, so I think we mentioned we want to be able to. Let me see. Hello, are you guys hear me or?
Yeah, I can hear you.
Okay.
Could you go into the presentation mode? It's easier to see.
Okay, slideshow. View.
Just on the bottom bar, I think. Just next to the zoom, and you have. Yeah.
Okay.
Yeah.
Okay. Thanks.
Brilliant.
Thanks.
Cool.
Okay. Thank you. So basically, given sample from a distribution, we want to be able to generating sample from another distribution right? So we want given a sample from distribution P, we don't know P, but we observe sample from this distribution. We want to be able to creating another distribution, that's the Q theta, whose parameter is theta, that if we draw sample from that distribution, this sample will resemble the sample we want to fit. For example, on the left side, there's an image. This is I think this is CIFAR 10 images. And we want to be able to have a model able to generate image look like this. On the middle part, you can see these are basically we can tell from from different distribution, but if on the right side, we can see the relatively well regeneration of the sample from P. Okay, so that's the basic idea. And how do we achieve this goal? I think what typically matters is what kind of network structure are you going to use to define your generator? And the second is what type of distance measure do you use to define how far away P and Q? So how do, as I mentioned, there's an important thing is how do you measure the difference between two different distributions? Okay, so looking by our eye, we know the distribution of the image on the second image are quite different from the distribution of the image on the first on the left side. But the question is, how do you quantify this difference? Okay, so another question that matters is how do we, once we define this distance measure, how do we optimize our generator to reduce this distance such that the Q will eventually match P? Okay, so this brings to the questions how to train a generative model. So in the history, the most common way we do is actually related to the KO divergence. So the two common way, one is using maximum likelihood estimation. You're going to typically define your Q as a parametric distribution, for example, Gaussian or Poisson, and then you're assuming the data is drawn from this particular type of parametric distribution, and then you're using maximum likelihood estimation to estimating the parameter of the distribution, which is basically the same as you minimizing the KO divergence from Q to P. Okay, so the P is the distribution you don't know, but you observe sample from it, and the Q is the distribution you're trying to estimate. Okay, trying to fit. And another way we do that's become also very popular recently is variational autoencoder. In the variational autoencoder, you can consider is a hierarchical structure. You have a decoder, you have a prior, and the question is how do you learn the parameter of this decoder and the decoder such that the marginal distribution can fit your data well. And that can also be converted into a problem of minimizing the KO divergence. Over there, the KO divergence, you're trying to minimize the KO divergence from between your variational posterior and your true posterior of your latent variables. So both maximum likelihood estimation and the variational autoencoder can be considered as in the framework of minimizing KO divergence between certain distributions. So if you're able to do that well, you're able to building a generative model. Okay. So another idea is rather than using KO divergence, we can go to Jason-Shannon divergence. And why we go to Jason-Shannon divergence, I'm going to explain very soon. Another idea that is Weierstein distance. Okay. So why we move away from the KO divergence, which very closely related to maximum likelihood based method, right? So essentially, we find out if you use a maximum likelihood-based method, typically you constrain yourself to analytical probability density functions, such as Gaussian, gamma, Poisson, etc. Okay, so in this type of model, typically we find out they are not going to producing very well regeneration of your data, especially your data is high-dimensional data like images. Okay, so even if able to generate something like image, it could be look very blurred. Okay, so that comes to generating very high quality, visually appealing image, and again turns out to be a very good solution. So again, instead of doing maximum likelihood estimation, it's basically changed to the idea of trying to minimize the distance between two distributions. So this distance is we will show is basically the Jason-Shannon divergence. Okay, and another key idea in this scenario is you're not going to using a parametric distribution such as Gaussian to define a generator. You're trying to using something called implicit distribution. Essentially, one way to define implicit distribution is you net a random noise, feed it forward, propagate it through a deep neural network. Then you end up with a distribution. Typically, you don't have the density function, but it's very easy for you to generate. For example, you feed a 10-dimensional Gaussian noise, you end up with a 256 by 256 image. So this is a not invertible transformation, so you don't get an analytical density function. Okay. So this has been shown to be providing very, very impressive performance in terms of generating images, but it does have a problem. We know it's typically difficult to train. It's very brittle. It's very easy to break. Okay. So in this framework, as I just mentioned, the first idea is you want to building a deep generative model, whose role is to map a noise to a high-dimensional data, such as natural images, and you want to also be able to define a way to measure the difference between your data distribution and the distribution you're trying to using a neural network to approximate. Okay. So one idea using Jason-Shannon divergence, which can be actually converted into a minimax problem. So you have a discriminator trying to tell whether the image is actually from the true image you observe, or this is the image that is generated from your generator. And then your generator is trying to then confusing the discriminator. So they are playing the minimax game, and you can prove when the discriminator is optimized, then this minimax loss essentially becomes the Jason-Shannon divergence between your data distribution and your fake data distribution. Okay. So one key for Jason-Shannon divergence is that actually it's related to density ratio estimation. So it can be considered as a special case of this F divergence family, and in which I want to point out there's a very important term is you need to estimating the density ratio of your data and your generator distribution. So this density ratio estimation is universal in the F divergence family, and for GAN is basically you need to when the discriminator is optimized, you're estimating the density ratio of log p over p plus q. Okay. So this brings a very, very clear issue is that you require your data distribution and your generator distribution to have overlapping support. Okay. So there are examples you can show that this requirement will fail in certain scenarios. For example, if you have a distribution P0 is one point is 0, another point is a uniform random number, and you're trying to approximate this distribution with a theta as the first location, also uniform random noise at the second location. And the Jason-Shannon divergence or KO divergence in this scenario does not work because the support of these two distribution will be different when theta not equal to 0. Okay, so this caused us to think about how can we go beyond the Jason-Shannon divergence or KO divergence, which require distribution to have overlapping support. Okay, so this brings to another distance I'm going to introduce is called the Wasserstein distance. Okay, so the Wasserstein distance, the one key distinction is it allows these two distribution P and Q to have non-overlapping support. Yes.
Could I have a question about the overlapping support? Because
yes.
I'm not working directly in statistics. So
yeah.
I wonder, is that the overlapping support mean the shape of the distribution, or what kind of properties of the distribution you mean here?
So let's say you have one distribution who is defined on is uniformly distributed between 0 and 1. Another distribution is uniformly distributed between 0.5 and 1.5. Okay. So then these two distributions, they have non-overlapping support. So right. So which means then which means if you look at this density ratio for some location px has density and qx right. equal to 0, then we say they have non-overlapping support.
Right. If I do, for example, if I do the whitening, I mean that's moving like everything to 0 mean and with a standard deviation and and record like that value before. I mean after. To generate like two whitened distribution, so they will become like two distribution with the overlapping support. Am I right?
So you mean if you whiten the image to a certain region and compared to the original non-whitened image?
Not just images. For example, if you have like two Gaussian distribution, one half the mean is 0 and standard deviation is 1, and the other is mean is 1 and standard deviation is 2, and you can just do the whitening on the second distribution and move it back to 0 and the standard distribution 1 before comparing them. So this one type of solution you can use.
Actually, for the Gaussian distribution, even they have different mean and standard deviation, they are not considering has different support because all this support is from minus infinite to infinite.
Okay.
No matter how small it is, you still have density. I would say if you have two distributions, one distribution at a certain point has density larger than 0, another distribution over there is exactly 0, then they don't share the same support.
Okay.
So you can see the problem is, let's say qx is equal to 0 at a certain point, but px is not equal to 0 at a certain point. Then this ratio would be infinite. Then that's the problem.
Okay, got it. Thank you.
Thank you. So thank you for the question. Okay. So feel free to interrupt me. Okay, if you have any questions. Okay, let's continue. So Weierstrass distance is a well-known example that it allows two distributions to have non-overlapping support, but you can still you can still have computing how different they are from each other. Okay, so this distribution is defined in a way. I don't want to go to too much detail. The basic idea, you want to define a optimal joint distribution between two distributions. Okay, so you have two different distributions. You want to define an optimal joint distribution such that the difference between the two can be minimized. You want to transporting from one distribution to another distribution, so you need to figure out a particular type of transport plan. Okay, the typical idea we think about is there is a pile of dirt follow certain distribution, and there is a certain hole on the ground also follow another different distribution. You want to figure out the optimal way to move the dirt to the hole such that the effort is minimized. Okay. So there's lots of literature and lots of different explanation about optimal transport and how it's become the Weierstrass distance. I don't want to go to the detail, but I want to emphasize it's the key is how are you going to finding this kind of optimal joint distribution that is describing how do you move from one distribution to another distribution. Okay. So Weierstrass distance, it's trying to finding this optimal joint distribution, but it's known in the literature that it also has a dual form. The dual form is basically you can representing in this formulation, and this formulation is saying that if you can finding a a Lipschitz function and finding the one providing the supremum of these two, then you're able to recover the Weierstrass one distance. Okay, so I also don't want to go to the detail behind why this is the case, but I want to bring your attention is you can consider the F is a critic. So the F is trying to maximize this difference, but when you're learning the Q to fit the P, you want to minimize this difference. So basically, this dual form, you can somehow converting the problem of trying to optimize the Q to minimizing the Weierstrass distance between P and Q to a minimax problem, because you're trying to find a critic to maximize this difference and trying to finding your distribution to minimize this difference. Okay. So that's some background information about the Weierstrass distance. And another way to think about the Weierstrass distance is we can take an empirical sample from two distribution. You take 100 sample from P, you take 100 sample from Q, and then you want to find the best one-to-one mapping between them. Okay, so you can imagine this kind of one-to-one mapping is a very difficult problem to do. For each time you're getting 100 from P, 100 from Q, you need to find an optimal matching between this one-to-one matching between them. So which could be extremely time-consuming. Okay, especially the size is increased. If you can do it in 100, think about if you have 1,000 data point from P, 1,000 data point from Q, you still want to try to find the optimal matching. That's going to be extremely more difficult. Okay, so people then figured out a simpler way to do this. They figure out you can put in entropy regularization, and if you put in additional regularization, then you can finding out iterative algorithm to approximating this kind of matching. Okay, but the take-home message is even if you do that, you will end up with problems. You have iteration inside iteration. So each iteration you take a mini batch from P and you take a mini batch from Q. That's then you do another iteration to estimating the difference. They call it synchron method. Okay. So it's basically even the Weierstrass has a very attractive property. It's difficult to estimate in practice. So this comes to a alternative way to estimating Weierstrass distance. So it's actually projecting Weierstrass distance into 1D. Okay. So because in one-dimensional case, if you have 100 data points from P, you have 100 data points from Q, the empirical Weierstrass distance between these two one-dimensional vector is basically just the sorting each of them from small to large, and then compare the difference, take the summation. That becomes the empirical Weierstrass distance between two one-dimensional vectors of the same size. So for this reason, people have been thinking about, well, then we can then basically projecting high-dimensional vector into 1D, and then I can somehow computing the difference. I can do this many times, and then taking the summation of these many different random projections, because each random projection gives me a difference. You take the summation of all these random projection, you're getting a something called a sliced Weierstrass distance. Okay. So sliced Weierstrass distance, as you can see, you may need to do tens of thousands of random projection to get a satisfactory performance. Okay. So that's why the additional method trying to finding, for example, finding the optimal slicing. And actually, I noticed actually the paper from exactly from VinAI, right? This is a Win 2020 paper. Is about how to better do the slicing. Okay. So this is about Weierstrass, how we can handle it to make it computationally feasible to deal with. Okay. So in this talk, so actually we want to go beyond the Weierstrass distance, go beyond the constraints of optimal transport. So let's remind you a key idea in Weierstrass distance is you want to find a optimal joint distribution between P and Q. So the joint distribution will have marginal respect to X is P, marginal respect to another side is Q, okay? So this optimal joint, having a joint distribution satisfies these two marginal constraints in practice is really difficult, okay? So this actually is one of the motivation for us to propose something called a conditional transport, okay? This conditional transport, the simple idea is instead of constrain both marginal to be satisfied equal to P or Q, we can only constrain it has marginal is equal to P, but on the other side, I don't constrain. Or I constrain on marginal respect to this to Y is Q, but I don't constrain is marginal respect to the other side. Okay, so that is a kind of simple way to state what we're going to introduce. So our motivation is we again allowing two distribution to have non-overlapping support. So Weierstrass distance can already do this, but I just mentioned it's computationally typically very challenging. We also want our distance to be simple to estimate and stable to optimize. We also want our model be able to support implicit distribution that have a low analytical density function. Okay. We also want to providing unbiased mini-batch based stochastic gradient. Okay. So this is the motivation I mentioned in the very beginning. Now I want to remind you why we're doing this, right? So now we want to. So now I'm going to tell you how we actually providing a conditional transport that be able to satisfy all four different motivations. So we define this conditional transport into make it to become directional, forward and backward. So we call it bidirectional. Okay. In optimal transport, there's no direction. Go from X to Y, Y to X is the same. Okay. But in conditional transport, we're going to have both forward transport and a backward transport. Okay. So let me explain the intuition. Okay. So first of all, we want to do forward transport. The forward transport is I want to transport a point from distribution of X to the distribution of Y. Okay. So and the idea is this cost will be small as long as your Y providing a good coverage of X. Okay. So intuitively think about the problem of demand and supply. Okay. So think about your X is your demand. Okay. So your Y is your supply. So to make the demand happy, as long as my supply providing a sufficient coverage of my demand will be happy, right? So think about you have lots of customer to shipping stuff. That's the demand. You have the shipping center. So as long as the shipping center, for example, you have enough post office around the country, no matter how remote is location, every customer in the nation will be happy because they have easy access to the post office. Okay. So from this point of view, forward transport is we want to transport data from X to Y, and as long as Y providing a good coverage of the density of X, then this transport will have small cost. Okay. The backward transport is different. Is the reversal. The backward transport is trying to transport from Y to X. Okay. So which means in the same analogy, the cost will be small as long as the X providing a good coverage of Y. In other words, as long as your Y concentrate around the mode of Px. Okay. Intuitively think about demand and supply. So as long the supply side is happy, as long it put its supply center closer to the highest demand, right? So it does not care whether it providing coverage to very remote areas because that's not the main source of revenue. So as long as they put in the supply center in the high density region of the demand, they will be happy. Okay, so which means this backward transport from Y to X, to reduce the cost of that, we are promoting the mode seeking behavior. Okay, so the mode cover and mode seeking we looking at how PY behave respect to the data density, which is PX. So if we combining them, is actually providing very interesting behavior. So let me give you some intuitive toy example. So this one, gamma equal to 0, is the case I'm only using backward transport. As you can see, the red curve is the density of the data of the true data, and the blue is the density of the fitted Y. As you can see, the Y basically concentrated around the mode of the X. But if you go other way around, if you only use the forward transport, you will see that your Y is trying to provide the full coverage of the density of X. Okay, and if you combine both to the middle, you're providing very, very good fitting. So let me show you another toy example. This is 8 different Gaussian. If you do the backward transport, it only capture one mode. If you do the forward transport, it's not only cover all the mode, but also putting extra density on where it's not supposed to be. Okay, which is you're trying to providing good coverage. Okay, you're allowed to providing density on the location is no data, as long as it covers well. And on the backward, you allow it to be missing lots of density as long as it can find a good mode. Okay, so this is a very, very unique property of conditional transport, which means you can provide controllable behavior of your fitting of Y, whether it's seeking mode or whether it's covering mode. Okay. So hopefully I have explained the intuition, and to implement this idea, then it's also actually quite straightforward. So you're going to represent your joint distribution in the forward side to be Px times pi Y given X. We know define a joint distribution. In optimal transport, you're trying to find the optimal joint distribution whose marginal over X is Px over Y is Py. Okay, but in the forward transport, we factorize the joint distribution to be Px times pi Y given X. Basically, a joint distribution is written as the product of a marginal and the conditional. It's very clear if you take the marginal, if you marginalize Y out, this is gone. You only left Px. So this joint distribution will satisfy the constraint on the left. If it's marginal over Y, you're going to recover Px. But if you marginalize X out, you don't recover the marginal distribution of Y. Okay, so that's the key. So here, this is the joint distribution. If you marginalize X, you get a Px. You marginalize Y, you get a Py. But here, you're only getting Px. You're not recovering Py. Okay. But if you do the backward, you factorize the joint distribution to be Py times pi X given Y. So it's marginal over Y. It's margin. If you marginalize X out, you're getting Py. But if you marginalize Y out, you do not get a Px. Okay. So that's the difference. So you relax the constraint. So the benefit now, the key point now becomes how do you define this conditional distribution, right? So I have the X marginal. I define what's the probability for X transported Y. So the intuition is you should have a higher probability to be transported to Y that are closer to you. Okay, so think X is the supply, Y is X is the demand, Y is the supply. So the demand will go to supply center that are closer to it, right? So that's very natural to think about. You go to the post office that closer to you. You're not trying to run 100, 200 miles to go to find a post office. So if you think about in that idea, then this is basically defining the D. You can think about is somehow measure the distance between X and Y, point X and point Y. If they are closer, then you tend to have a higher weight. So if you renormalize it, you define a density. Okay. Similarly, you do that for pi x given y. So the problem for this this part is these two conditional distribution actually in general is intractable to compute. We do have special cases we show if the prior distribution is conjugated to the likelihood, this can take closed form. But this is only happens in very special cases. You need to put a very strong constraint on how your d phi xy looks like and how your prior looks like. So that beats the purpose because we want this to be very flexible. Now you need to put a very strong constraint before for this be able to work. Okay, so which is not ideal. Okay, so but I'm going to provide you a solution for that. Okay, in a minute. So in summarize, we define this forward and define this backward transport, and intuition is the forward is going to promote a mode covering behavior, and the backward, if you minimize the backward, is going to promote mode coverage behavior, mode seeking behavior. If you combine both, you're providing a very good compromise between these two different behavior and providing strong resistance to mode collapse or mode collecting. Okay. So, yes, any questions?
Yeah, if you compare this like forward and backward with the Jensen-Shannon distance, the Jensen-Shannon distance actually like an average of KL diversion PQ and QP, right? And in your case, you show that if you use lambda is equal to 0.5, it's actually it's like 1/2. It's quite equivalent to the Jensen and Shannon theory as well. Any comment on that? How is different between the forward conditional transport with the Jensen-Shannon?
So in Jensen-Shannon divergence, right? The Jensen-Shannon divergence is EP. Let's say EP log P over P plus Q, and plus EQ log Q over P plus Q. So over there, you need to estimating P over P plus Q, this density ratio, right? So this density ratio needed to estimate. But from in the forward, in neither forward or backward, you never needed to estimating this density ratio. So that's one key difference. Okay. If you needed to estimating the density ratio, then you have to have overlapping support. But in the forward and backward transport, you don't require X and Y to have the same support. Does that make sense?
So it means that you don't need to estimate the data distribution. You only need to estimate the modal distribution. In this case, is the P y given X and P X given Y. Is that what you mean?
Yeah, we only needed to building this conditional distribution. And this conditional distribution is not the density ratio between Y and X.
Okay, so for example, in the second bullet point, the forward CT, for two expectation, it means that you only need to estimate the expectation of, I mean, the second E. Is that right?
That's right. You only needed to estimating this expectation. To estimate that, you only needed to be able to draw from this conditional distribution. So you only needed to draw from X and then draw from this conditional distribution, and then you can estimate in this forward CT.
Okay, cool. Yeah, okay. That's good. Thank you.
Thanks. Yeah, actually, I will mention very soon how we actually draw from this distribution. I mentioned this distribution, unless it's a special scenario, you have analytical conditional posterior, so you know how to draw it. In the general setting, actually, you don't have a tractable form for this one. So then we need to find a way to approximately draw from this, okay? Which I'm going to introduce very soon, okay? So, so there's some property basically showing the CT is actually a divergence when the navigator with this phi parameter is optimized, okay? And they basically it can become Weierstrass distance subject to certain condition, okay? But in general, it does not require this pi which is the joint distribution to satisfy this two marginal constraint. Okay, so it's I would say it providing opportunity for faster computation. Okay, or also more flexible. So
sorry, there's just one more thing. I just remember for example, if you use a Jensen channel, you can actually compare like all of the properties of two distribution. Okay, for the conditional transport, you only compare like the mean of the distribution. So it doesn't go to the shape of the distribution will be similar. Am I right?
So actually, we are not comparing the mean. We are. It's not comparing the mean. It's not like a mean embedding kind of thing. It's not. It's more like it's more
a first order drawing.
Yeah, I would say it's more closer to optimal transport. Okay, let's say you have two sets. In optimal transport, you need to do optimal matching. Here is more like you're trying to finding a conditional mapping, and it's not compared to mean. Okay.
Okay. Cool. Thanks.
Okay. Thanks. So when I show you more detail in later, probably that will become more clear. So we have two distribution, but in reality we don't know the analytical density function. We don't know the tractable form of this conditional density. So how do we deal with this problem, right? The way we deal with that, first, in real world, for your data X, you're only getting empirical distribution, right? For your Y, because you don't know the density, so typically you also approximately represented it with a bunch of random sample you draw, and they approximate it with the empirical distribution. You draw MIID sample, and now you're approximating your Y distribution using this. You draw n random sample from your data and approximating your data with this empirical distribution. Okay. So this is actually how we're going to define the forward and backward transport. We now call it the amortized conditional transport. So it's a approximation to the conditional transport using mini batch from the data. Okay. So I want to bring to your attention is first, to computing the forward transport, I'm going to draw a random point from my X, and then I'm going to define a conditional distribution from this point to my Y. So now I already replaced my Y distribution with m data points. Okay. So actually this should be pi m. Okay, sorry for the typo. So the pi m is the probability for X reaching any one of them. So think about it, you have one customer here, that's the demand. There are m different supply center. So this customer needs to go to choose which supply center is going to go. The way they're going to choose the supply center is using this probability. It's computing how far away it is to supply center J, and then you take the exponential minus of this distance, take the normalization. So which means it will make you easier for this customer to go to the closest supply center. Okay, so that's the transport probability, right? Okay, and that's it. So basically, you draw a X from your data distribution, which give you a customer, and this customer is going to go to one of the supply center. So you randomly draw m supply center to representing your supply distribution, and now this formulation would be providing your expected cost of go from a data in X to distribution in Y. So this is the cost in forward transport. Okay. So similarly, you have a supplier trying to reach his customers, trying to reach the demand. So you initialize n different demands, and the supplier needed to fulfill the demand in this n different location, and it will reach his demand that's closer to it with a higher probability. So that's also the intuition. Okay. So combining both, you end up with something called a amortized conditional transport divergence. Okay. So why we took the name of amortization? So think about in optimal transport, if you're doing Weierstrass distance and you approximate the Weierstrass distance using empirical samples, you draw 100 data points from X, you draw 100 data points from Y, you finding the optimal matching, that's your optimal transport, that's your Weierstrass distance. In our scenario, you also draw 100 sample from X, 100 sample from Y, but your navigated parameter here is taking care of the computational optimal matching. Okay, so in Weierstrass, every time you're getting a mini batch, you have to recomputing the optimal matching. But for conditional transport, such computation is completely avoided by learning this parameter phi. So once you have the mini batch, the transport probability is already given to you, and then the computation is just a simple pairwise distance computation and this probability computation. Okay, so the computation is significantly reduced, and make it practical for us to handle large mini batch size. Okay, and also even for small mini batch size, this amortization also providing advantage to smoothing the mapping. Okay, so you become robust to, for example, outliers. We know in Weierstrass distance, the computing of the sample Weierstrass distance, they are not robust to outliers. Okay, with the amortization we introduce, it become quite robust. Okay, so given the time constraint, so how long do I have for the talk?
Yes, maybe another 10 minutes.
Okay.
I think you should ask the host of the talk, Ms. Lin, I guess.
Okay, I will try to go quick. Okay. So basically, I think I get into the basic idea is using a conditional transport to replacing the optimal transport, which bring the advantage. One thing is computation, and another thing I want to introduce is it's actually quite easy for us to add in a critic into the conditional transport. So we know the pixel for high dimensional data, the pixel-wise difference, for example, for image, the distance in the original data space is not that useful as a way to measure the difference. So we typically need to introducing certain kind of feature embedding. Here we call the critic. So this critic is essentially providing a way to embedding your original data into certain space, and in which space the difference will become meaningful to measure the difference between your high dimensional data. Okay, so we call it the critic. So this critic can be introduced into the conditional transport framework, and the role of the critic is basically trying to maximizing the cost of transport, not only from point to point, but also trying to distort your transport plan. Okay, so and we are going to then transfer the problem to minimax. So you optimize the critic to distort the point-to-point transport, and also the transport plan, and you're trying to optimize your generated parameter and the navigated parameter, which is the parameter used to computing the conditional transport probability to minimize this cost. So we find that if you do this, then you are fine with high dimensional data. So for low dimensional data, you don't need this. Okay, if your distance in the original space is meaningful, you don't need to do this. But for high dimensional data, you definitely need to do this. Otherwise, you're going to not able to getting realistic images. Okay. So, and also we show a important thing is we providing a unbiased estimate, gradient estimate for the ACT divergence, which is asymptotically unbiased for the CT divergence, which is the limit when your median batch size goes to infinite. Okay, and this is a one-dimensional example for which case we do have analytical form of the conditional transport plan from both forward and backward. So this is a special example. Your PX, your true data is normal 0, 1. Your fitted data is normal 0 exponential theta. So theta is trying to learn, and you define your distance. You define this navigator to be the difference in the x minus y squared divided by 2 phi, and you define the transport cost to be just the equilibrium distance. And then you can show you have analytical forward, you have analytical backward, and you also have analytical divergence of the forward and backward divergence. Okay, and if you show you're minimizing the summation of these two, you end up with being able to recover theta, whose ground truth should be 0. Okay, and this also providing idea. If you only do the forward divergence, as you can see, the forward divergence is really happy as long as the theta is larger than 0. Theta larger than 0 imply this variance is larger than 1, which imply mode covering. Okay, if you're only using the backward, the model is pretty happy with theta anything smaller than 0. Theta smaller than 0 means the variance is smaller than 1, which imply mode seeking, because this one is going to be more picky than the true data at around the same mean. Okay, but if you're combining both, it's very clear theta equal to 0, around 0 is the optimal solution. Okay. So also we apply this for to fit 1D Gaussian mixture, and so this is the red curve is the true data, and this is showing how you're optimizing the amortized conditional transport, how your performance improve as the training progress. Okay, and eventually you can see the fit reach data density really well. Okay. And another example I just mentioned is it compared to sample versus time. We have an advantage is that we have an amortization scheme. We make it be robust to the mini batch size. So if you have a sample versus time and using sample versus time to guide your learning of the generator, it does well when the mini batch size is as large as 5,000. But once you reduce to 200 or even 20, you can see the performance quickly deteriorate. When it's equal to 20, the performance is basically not able to faithfully recover the original data density. But for our algorithm, no matter what's the mini batch size, it does almost equally well. Okay. So we also mentioned another example is for two-dimensional data set. And this is a half moon data set, is a challenging 2D data set to fit. If you're using GAN, it's very easy to mode collapse. Okay, for example, at a iteration 15K, we freeze the critic, freeze the discriminator, then it quickly deteriorate, become mode collapse. And this happens as well for Weierstrass GAN with gradient penalty. And it's okay for slice Weierstrass GAN. It's also okay for us to freeze our critic or freeze our navigate in this scenario. Okay. Similarly, for other example, for 8 Gaussian as well, we have similar type of observation. And this is another example to show if your true data you have 8 mode, but this one mode is much smaller, or one mode is much larger. This is the true data density. Okay. One mode is much smaller, one mode is much larger. And we show our algorithm can do well recovering, but the other comparing algorithm, they're not doing well. They either mode collapse or providing data points on locations where there's no true data density. Okay. So continue, this is, I'm skipping these slides. Let me show you some real images. So this is applying our method for real images. This is CIFAR 10. This is Celeb A 64 by 64 resolution. This is LSAN 64 by 64 resolution. And then numerically, we show we are improving both existing methods. So we're basically using the DC GAN backbone, but we swap its Jason-Shannon divergence with our statistical distance ACT, and we also apply to spectral normalizing GAN. We swap its distance with our distance, and that we show clear improvement in all this scenario. For example, 21.5 to 17.2. So the structure is exactly the same. The only difference is we swap its difference with our distance. Okay. And this is an additional example on S on 128. This is high resolution, and this is for face images, celebrity high resolution images. Again, this is on S spectral normalization GAN, just swapping its statistical distance, nothing else changed. Okay. And this is something I already mentioned, is about the balance between mode seeking and mode covering behavior. And this is we also done on administered digit. If you only do the backward, actually, we know backward is mode seeking, so it's not providing anything. Actually, forward is actually works, and combining both, it works equally well in this particular scenario. And yeah, we have additional ablation study to show that the critic we use can be pre-trained or trained with a different loss. So I want to emphasize in existing method using the critic, for example, GAN using the discriminator versus stand GAN using the critic need to be co-adapted for the generator. If you freeze the critic or train it too fast or too slow, what happens is your algorithm basically diverge or breaks down. But for us, the critic is providing a role is not super important. You can use a pre-trained critic. You can freeze it anytime during the training. You can train it with a different loss, and it all works. Okay. Yeah. Let me jump to the conclusion. So I want to emphasize the amortized conditional transport. The conditional transport is a way that allow us to measure the difference between distribution with non-overlapping support. It's easy to computing with mini batch, and it's able to compatible with existing GAN and the Western GAN by just using exactly the same architecture but swapping the final distance measure used in existing structure. Okay. So there are also many future work we are looking forward to investigating further, like more theoretical understanding what we are doing, and also whether it can be connected to like contrastive learning, whether it can be connected to attention mechanism to providing additional regularization. So all these things we have ongoing work, and we have actually very promising initial results in terms of putting ACT as a very flexible constraint and easily compute constraint in places where difference between distribution could play an important role. Okay, so that's all I want to say. So I'm happy to taking any questions you may have.
Hi, Dr. Zhou.
Yes, hi.
Yeah. So I have a question about the metricity of CT and ACT. So as I understand, CT is a diversion between two measure, but the ACT is just ACT is just an empirical version of CT, and it's just an asymptotic converse to the CT. Then
that's right.
It's not kind of proper diversion between mu and u, right?
Yeah, that's a very good comment. So you can think about when we talk about expected sample versus time, right? So expected sample versus time is kind of asymptotic approximation of the true versus time. You can think about the ACT is also asymptotically approximation of the CT, which we prove actually is a divergence. So if you're using the ACT itself, it's not necessarily a divergence. I agree, because even mu and v are the same, and the expected the ACT may not equal to 0. Okay, unless you define the unless your focus is on compare on discrete distribution. If you have two exactly same discrete distribution and the ACT definition, and with optimize the parameter of the conditional of the navigator which define the condition, distribution. Okay, but in the common definition, it's defined as expectation respect to the continuous distribution. So I think it's the same as the sample expected sample versus time. I don't think it's a proper distance. But I don't think that prevents you using it as a way to somehow to reflect how far away two distributions are, right? So we're trying to our empirical evidence show it works, and we definitely need to have more theoretical understanding on whether it's actually a true distance measure or how far away is from a true distance measure. Okay, thanks. Does that answer your question, Kai?
Yeah. So I have another question. So
sure.
So why don't you put the mean over 5 on the definition of CT? So it's like putting we choose the optimal 5 for the distance. Do you understand my question? So like in optimal transport, right? We want to find the optimal transportation plan. Why in CT we don't want to obtain the optimal one, like in the formulation, in terms of formulation, not in the empirical. You want to minimize, but like in the formulation, why you don't put?
It's a very good point. It's a very good point. Okay, so if you look at the 1D case, for the 1D case, we have exactly the CT. We can compute in the analytical form. So the phi is providing a assisting role. If you make phi goes to optimal solution too fast, then you lose the ability to learn theta. Okay, so if you're checking how it works, so if the phi, the optimal solution is 0, but if you make phi go to 0 too quick, then there could be your gradient of theta is still correct, but it's very, very small. So it's not guiding you towards the optimal solution fast enough. You may take a very long time before you reach the optimal solution. Does that make sense? That's for the CT. Okay. For the ACT, between different mini batch, right? So the phi is providing certain kind of smoothing, okay? Because it's actually, I think it's kind of built-in mechanism to fight like outlier or fight to be building robustness. So there's lots of interesting things we're still trying to understand better, okay? And I welcome any suggestion or comments on that. And at this moment, we have certain empirical evidence to show how phi is helping. Why we don't want phi to reach the optimal solution instantaneous, right? So there's some empirical reason we find that why we want to slowly converge to the truth. Okay, don't want to go too fast, or even we don't want the optimal phi. We can just make phi to be to stop. In our experiment, actually, we show the navigator can be stopped at any time as long as it's reasonably trained. But yeah, but in the CT become a divergence only if the phi is optimized. If phi is not optimized, it's not a divergence, but it works better than if you make phi to be optimized in the very beginning. Okay, so that's something we find out, and we're not exactly sure that's correct yet, but that seems our experiments indicating that's the case. So definitely we need a more theoretical analysis, and we'll welcome any suggestion you may have. Okay.
Thank you for the answer. Yeah.
Thank you. Any other questions?
Just one more thing. Yeah. So could I think about phi as a function, right? So it's currently a parametric function with
that's right.
Theta. Okay.
Yeah, it's basically a neural network. Input is let's say your input is x, your output is scalar. That's basically a neural network. Or you input the difference of x minus y, and you go through phi, you're getting a scalar. So it's we define as a neural network. The phi is the parameter of a neural network.
Okay. Okay. So, but with the neural network, you will have the constraint in the network architectures like how much weight and how much layer you can put in. So have you ever thought about moving it into the non-parametric function?
That's a very good comment. We haven't thought about that yet. We are at this moment we basically trying to somehow mimic the existing discriminator structure. Right. So the existing method find a certain type of discriminator structure or critical structure that's providing good way to mapping, because the critical the discriminator is mapping high dimensional data into scalar. So we basically borrow that structure. But I think there must be other way, like a non-parametric function to replace it. And I think that would be also very interesting thing to investigate. Thanks.
Yeah, and I'm thinking about the relation between the critic function and the transport function. Are they related in a compositional way, or is?
Yeah. So the critic is trying to maximize, and the transport is trying to minimize. So the navigator, we call the navigator phi, is trying to minimize. Yeah. So there are two ways to do that. One is your critic is not messing up with your navigator. Your critic is only trying to distort your point-to-point distance. Another way is your critic is actually also messing up with your conditional transport probability, because you can let the data pass the critic, and then you take the difference of that, it goes through the navigator. We try both solution. The second solution actually works better for high dimensional data. For low dimensional data make no difference, but for high dimensional data, you let the critic to mess up with not only the point-to-point distance, but also messing up with the navigator with the conditional transport. We find that to be performed better for high dimensional data.
Yeah, so it means that it's a compositional relation. If you have a f of critics and open parenthesis f of transport and the data, okay, and you train it simultaneously.
Yes, we train one with gradient ascent, and then another with gradient descent, and back and forth.
Yeah, cool. Thank you.
Thank you. Yeah, so one thing I want to emphasize is I mentioned a little bit in the end of the talk is so in GAN or in Weierstrass GAN, the critic play a very important role, because it in theory needed to be optimized for you to reach your true objective, which is either Jensen-Shannon divergence or Weierstrass distance. But in practice, your critic really needed to be co-adapted with your generator. For example, if you train it too fast, train too slow, or just freezing it, it's not going to work. Typically, it breaks down very easily. But for us, the critic is just providing a way to help you learning better in basically more like trying to learn in a different feature space, right? So we can basically using a pre-trained critic or freeze it or stop training it at any time we want, and the algorithm all works. Okay. So I think that's a very important distinction.
Yeah, that's good. Thank you.
Thank you. Well, any other question? If you have any other questions, so feel free to reach me by email. And I think well, Nyat and Kai are both coming to. Nyat is already at UT, and Kai is coming to UT. So I think it looks like there's a very strong connection between AI and UT now. And so if you have any questions, so feel free, or any suggestions, feel free to reach me. I think there's lots of things in this framework I don't know, and I really looking forward to experts to help me to look into further, to understand it better. Okay, thank you.
Thanks a lot for your talk.
Thank you.
Thanks, Ming. Thanks, Ming, for the talk.
Yeah, thanks, Ming.
Thank you. Bye.
Thank you so much, Professor, and thank you everyone for joining today.
Thank you very much, guys, and enjoy the rest of the day, and taking care. Bye.
Bye, Ming.
Bye, everyone, and see you next week.